Okay, so I think we can start with the first speaker of today, which is Simon Schreyer, and he will tell us about alpha prime correction to KPV, an uplifting story. So Simon, please.
Yes, thanks a lot for inviting me. And of course, thanks a lot for organizing this very nice seminar series. I'm happy to speak today. I will present my recent work together with Brane-flux that appeared in December last year with the title Alpha Prime Corrections to KPV. Let me check. No, I cannot move. Yeah, no. Okay, so one of the most important, or arguably most important questions of string Pheno still remains the question whether we can achieve controlled accelerated expanding universes from string theory. And one possible solution how this could be obtained is by controlled metastable de Sitter vacua, which is usually achieved in a two-step procedure. The first step consists of constructing a scale-separated 4D ADS vacuum with stabilized moduli. This is already a highly non-trivial step, but for the sake of this talk, I assume that this is possible. And then the second step is to uplift this ADS vacuum to de Sitter. And the most famous example how this can be done is the anti-3-brane uplift, which will be the main subject of my talk. And recently, there has been some analysis of alpha prime squared curvature corrections to the D-brane initiated by Daniel Junghans and to the NS5-brane in a paper together with Arthur Hebecker, also from last year, which with the result that they were threatening the classical stability of the underlying KPV process. There was one caveat to that story, and the caveat was that only curvature corrections were calculated, but there are actually hundreds of more terms at the same order in alpha prime, which include gauge fields and fluxes. And the main goal of the talk today will be to calculate these alpha prime corrections. To understand this in more detail, I will first explain what the Klebanov-Strassler throat is and how the KPV process works, and then we'll calculate the alpha prime corrections to the KPV process and discuss the implications for Pheno and also a new uplifting mechanism that emerges in that story. Okay, so the Klebanov-Strassler throat is used for the anti-de for the uplift using the anti-3-brane to avoid a runaway of the volume modulus and to decrease the contribution, the positive contribution to the vacuum energy. And one feature of this throat is that its metric is known explicitly, and the throat can be described by three cycles: an A cycle on which we can put m units of F3 flux. And a B cycle, which extends over the entire geometry, on which we can put k units of H3 flux. And then the anti-D3-brane contributes its tension, and due to putting the anti-brane at the tip of this KS throat, there's also this exponentially small warp factor, which we can achieve when we tune K and GSM appropriately. And then to achieve a small positive vacuum energy, we want that approximately the size of the ADS minimum is as big as the uplifting term. So what we need is that this flux in the throat should be much bigger than GSM squared to obtain, to have sufficiently large warping. This will also be important later. But putting just P antibranes at the tip of this throat is a little bit too simplistic, because it is known to the Brane-flux annihilation process discovered in the paper by KPV, is that there is a classical decay process of these antibranes. To understand this, we should note that at the tip there is the A cycle coincides with an S3, which can be described by an S1 fired over the S2, and so the S1 can be parameterized by this angle psi. So at the south pole, psi is 0, and at the north pole, psi is equal to pi. And what then happens to these antibranes is that they form an energetically favored state, an NS5 brane, which then wraps this S2 inside this S3. And this NS5 brane has a non-trivial potential depending on where it wraps this S2. And this is mainly due to two effects. So first, there's the effect from the the metric, from the tension of the brane that tries to pull the brane towards the south pole to psi equals pi. And there's a contribution from the S3 flux, which lives on this S3, which tries to pull the NS5 over the equator towards the north pole. So depending on the number of antibranes and the flux on this S3, this NS5 is either metastable, which is unsuitable for uplifting, and the uplifting energy looks like this, or the NS5 is classically unstable. Then the NS5 slips over the equator, annihilates with flux, and forms a supersymmetric state consisting of M minus P D3-branes at the north pole. Let us now look at the potential in a little more detail. So this is the potential following from the leading order action of the NS5 brane. It can be understood as in terms of these two main parameters, GSM and P over M. If we just pull out a 1 over GS squared factor from this potential, and there are terms coming from the F2 flux living on the NS5, from the C2 and B6 terms, and also from the metric. Graphically, the potential looks like this. I plotted it here for different values of P over M. So if we increase the value P over M, the energy barrier here decreases until we find that the NS5 just rolls down this potential and forms does not form a metastable minimum anymore, which would be suitable for uplifting. And we find this precisely at the value P over M smaller than 0.08. So in order to be able to uplift, we need to ensure this metastability condition. And just to remind you, there are two important scales in this process, which is, first of all, the radius of the S3 at the tip, which goes like GSM, and the radius of the NS5, which goes like square root GSM times sine of psi. And to emphasize again, this is a leading order analysis in alpha prime, so only takes into account the leading order action. So this story seems to be quite nice. So why should we study the effect of alpha prime corrections to that potential here? And the reason is twofold. So first of all, the metastability condition per se is interesting, because it would be interesting to see how alpha prime corrections affect this bound P over M smaller than 0.08 that KPV has derived. And the second point is that for Pheno, more specifically for a large volume scenario Pheno, the lower bound on GSM squared is very important. This can be seen in the following way. A few slides ago, I showed you how the warp factor depends on the flux numbers and GS. And we have seen that in order to obtain a consistent uplifting to small de Sitter vacua, we should require that the flux is much bigger than GSM squared. But this flux in the throat contributes positively to the tadpole. So due to tadpole cancellation, we need to cancel this by a negative contribution. And this negative contribution to the tadpole is usually limited, especially limited in type 2b constructions. So the smaller this quantity GSM can actually be, the smaller also the flux in the throat can be that we have to put there, which is then good to be able to cancel the tadpole. Let's see what kind of bound follows from the KPV analysis for the quantity GSM squared. We have seen that P over M should be smaller than 0.08 for the metastability. And additionally, the quantity GSM, which is proportional to the radius of the S3 at the tip of the throat, should be bigger than 1 to control alpha prime corrections. If we then choose the number of antibranes to be 1, then we obtain that GSM squared should be bigger than 12. So this is the bound from KPV. How can we now intuitively understand why alpha prime corrections will be important for this lower bound? This can be seen by considering intrinsic curvature corrections, because they will be suppressed by the radius of the S3 to the 4th power, which is proportional to GSM squared. That means that these curvature corrections will become important in the regime where GSM is small, and hence also GSM squared is small. That means that we are precisely in the regime which is interesting for Pheno. Also, the higher order alpha prime corrections become important. that means it's important to quantify what it actually means to be in control of alpha prime corrections. So we would also already anticipate that this that in this regime of small GSM squared also these alpha prime corrections become important, and this also generalizes to the flux corrections. Okay, so let's study the literature and see what we know about alpha prime corrections to Dp-branes. And we find that there are many, but not all corrections at order alpha prime squared are known. There are curvature corrections, which have been already calculated to the NS5 brane in our last paper. And these corrections are due to Brane-Green. And then there are also flux correction by Garuzzi and his students, and also in this paper by Robbins and Wang. And for our purposes, the important corrections to the D5 brane read schematically like this. So I omitted all the contractions between the fluxes and curvatures and so on. So there are actually hundreds of terms with different contractions, but just for simplicity, I suppressed this. And we see that there are corrections, the curvature, which we have already accounted for. Then there are flux corrections, mixings of flux and curvature, mixings of gauge fields with extrinsic curvature, and also more complicated couplings. Also, the Chern-Simons action is corrected, and there also F5 and FF7, for example, shows up. And epsilon 6 here is the Levi-Civita symbol. Okay, there's one problem in that discussion so far, because what we actually want to calculate are corrections to NS5 branes and not to D5 branes. Because the anti-D3 branes at the tip of the KS throw, they path them to an NS5 and not into a D5 brane. And I have to warn you that the following, what I will discuss in the following, is not a proof, but it only seems very plausible that the correction to the NS5 branes look like I will explain they should. But if one is not willing to trust this, one could also work in the so-called S-dual throw, where the anti-branes puff up into a D5 brane, which is discussed in this nice paper here. And our argument how to obtain the corrections on the NS5 brane is based on the following assumptions. So first of all, we assume that the action of a flux D5 brane, which is wrapped on an S2, should give back the action of a stack of D3 branes in the limit when we shrink this S2 to 0 size. This is due to the Myers effect. And then we assume that the action of the anti-D3 branes should be invariant under S-duality. This is shown at leading order in alpha prime and conjectured for curvature corrections by Brane-Green, and also generalized to other couplings, including fluxes by Garuzzi. And then, assuming these two things, we just S-dualize the corrections on the D5 brane, and they should yield the corrections on the NS5 brane. Let us be more explicit and look at, again, the curvature corrections, where we know that how the actions on the D3 brane look like. This is from the paper Brane-Green, where they write down this S-dual invariant action for the D3 brane, and E1 is an Eisenstein series, so it goes as leading order like 1 over GS. And then we take the first assumption and write down this action to the D5 brane, which is now fluxed. And we conjecture or find it very plausible that there should also be this Eisenstein series here, because if we now shrink the S2, we precisely obtain also the Eisenstein series here for the D3 brane. So we know, of course, the leading order correction in GS for the D5, but not the higher loop alpha prime, the higher loop corrections to alpha prime squared corrections, which are incorporated by this Eisenstein series. So this Eisenstein series here in the D5 brane action is not proven so far. But this is what we assume. And then all we do is we just S-dualize these corrections, including this Eisenstein series, and obtain this curvature correction on the NS5 brane, now written in string frame. And we see that the leading order term goes like 1 over GS squared, just like the tension term of the NS5 brane. So we find corrections in which scale the same way in GS as the tree level action of the NS5, which we find is very, very plausible. And this can also be extended to all the other couplings that we calculate. And what we then find is this quite ugly looking potential. In green, we have the tree level KPV terms, and in red, we have the curvature terms, which were already calculated, and all the other terms are due to the flux corrections and the alpha prime corrections we have taken into account in our paper. And these numerical constants C1 to C8 are explicitly calculated because we know the precise prefactor of these terms. And this potential again enjoys an expansion in GSM and P over M, as it was also the case for the leading order terms. We find that this potential has divergent pieces due to this cotangent, for example, which is due to extrinsic curvature terms. And also this 1 over sine psi terms, which come due to C2 and F2 couplings. So we find divergences at psi equals 0 and psi equals pi. But to look at this more graphical, let us just plot this potential for example, for fixed GSM to be 20 and different values of GSM and P over M. And on the right-hand side here is the tree level KPV potential, just for comparison. And we find again that the energy barrier here decreases when we increase the ratio P over M. And the metastable minimum goes away for GSM equals 20 when P over M is 0.07. So this is a very slight modification of the tree level KPV analysis. A new feature of this potential is that the minimum occurs at 0, negative, or positive values. And this will be important later for the new way of uplifting that we propose. And we see already these divergences here in the potential. And I will discuss these in a second. But so far, I mean, this potential is only for fixed value of GSM. So it would be interesting to see what happens if we scan the whole region of parameter space, look at all kinds of values of GSM and P over M, and see whether we find a metastable minimum suitable for uplifting. And in the blue region here, we do not find this metastable minimum. And in the yellow region, the minimum occurs at positive values, and in the orange region at negative values. So on this black line here, the minimum occurs precisely at 0 energies. This line here asymptotes towards the KPV bound P over M equals 0.08. So if you go to large GSM and large P over M, we recover the leading order analysis again. And then from the Pheno perspective, it's interesting to ask what is now the minimal bound on GSM squared that follows from our alpha prime squared corrected potential. And for this, we just go precisely towards this point here. So we want to have a positive contribution at the minimum. That's why we go here and to as small values of GSM as possible. And then we find that GSM should be bigger than 3.6. And together with P equals 1, we find that GSM squared is bigger than 144. So this is already a huge difference compared to KPV, which has GSM squared bigger than 12. But we have seen already that the potential has some peculiar features. It is divergent at psi equals 0, at psi equals pi. So it would be very interesting to discuss where we actually trust this potential. And first of all, the F2 couplings are very special because they scale like this here. And if now psi is order 1, then this 1 over sine squared psi is order 1, and also this term here is order 1. That means that if psi is order 1, this GSF2 couplings, they scale like a minus m minus p over m. And this is order 1 in the regime of KPV, where p is much smaller than m. That means that we lose trust over these F2 couplings close to the equator, which first of all seems very bad because we lose trust in the region right to the right of psi order 1. But this is not so bad because we anyways expect that as soon as the NS fivebrane wraps in S2, which is close to the equator, it anyways decays into the SUSY minimum at psi equals pi. So we are not interested in that parameter space of psi. Then we have to discuss the divergences at psi equals 0 and psi equals pi. And we assume that they should be cured once one sums over all higher order alpha prime corrections. And the reason is that at psi equals pi, we assume that there should be a SUSY minimum, which is 0 or negative energies. So this should clearly not be divergent. And at psi equals 0, we assume that this should asymptote towards the potential or the alpha prime corrected potential of the p anti-branes, which is also not divergent. So there is at least some indication that these divergences should be cured in the end. But there's also a main control parameter of this whole potential, which we identify to be GSM times sine squared psi, which is basically proportional to the radius that the NS5 brane wraps at the minimum. And here in this plot, I plotted contours of constant GSM sine squared psi. And the red line is the line where the energy at the minimum is at 0 value. So that means that if we are close to that line, the contour here is where the quantity GS times sine squared is order 1. So we actually need to include all higher order alpha prime corrections when we go close to this red line here. That means that we lose trust for smallish values of GSM and psi. Okay, what does that mean now for Pheno? We have already seen that this quantity GSM squared is now bounded much more strongly. So we require much more flux in the throat, which for consistent uplifting in the LVS then also needs much more negative contribution to the tadpole, which we need to cancel. The most optimistic bound was GSM squared bigger than 144, but this occurred very close to this red line here. So this is in a regime of bad control. So we should actually, for control of alpha prime corrections, increase GSM squared. So this is only the most optimistic case. And very briefly, we can also using the parametric tadpole constraint quantify how big this negative contribution to the tadpole should be for the LVS using the standard anti-D3 brane uplift. And we find that the minimal tadpole should be order thousands, which is very constraining because the currently highest constructed tadpole is of order 3000. As a last slide, I want to discuss this new way of uplifting that we also propose in this paper. And we have already seen this plot a couple of times now, and I already said that by tuning the alpha prime corrections, one can tune the value of the KPV potential at the minimum from negative to 0 and to positive values. This is a new effect. So if we go exponentially close to this black line here, this is again the contour plot of or the plot of the whole parameter space. If we go arbitrarily close to this black line here, we can uplift without tuning or without this exponentially large warp factor to warp down the tension, because we can make the effective tension, so the potential at the KPV minimum exponentially small by itself without having to rely on this exponentially large warping. This means we can sidestep all these issues related to large fluxes and large negative contribution to the tadpole. This is something which is also or not only applicable in LVS, but also in KKLT. But as it is usually the case for seemingly working uplifting mechanisms in string Pheno, we find ourselves in the regime or at the very boundary of control, because as I also showed this plot already, we have to go arbitrarily close to this red line here, where also higher order corrections become important, since this quantity GSM times sine squared psi is order 1. So this mechanism works at the very, very boundary of control. And that brings me to the open questions of this analysis. We should improve control by calculating even higher orders in alpha prime, which is of course very difficult because they are not known to the D-branes and also not known to the fivebrane, of course. And we can also study this whole setup from different perspectives, like for example from the non-abelian stack of branes, which is something which would clearly be interesting to do. And also studying the holographic picture would be very interesting, but it's of course also very hard. And then there's also a lot of literature on the back reaction effects, which we also have completely neglected so far. Yes, and this brings me to my conclusion. What have we done? We calculated many different alpha prime corrections to KPV with the result that they are very constraining for the LVS with standard D3-brane uplift, since this lower bound on GSM squared is much higher now. So we require much more flux in the throat. Moreover, we have proposed a new way of uplifting, which circumvents these constraints, but this way of uplifting works only at the very boundary of control. That means we need to improve our understanding precisely in this region of parameter space of the small GSM regime by studying this setup from different perspectives. Thank you.
Thank you very much, Simon. And do we have questions?
Can I ask you something? Have you looked at in the S2 picture with have you looked into this uplift mechanism? Do you know what happens there, like with the D5-brane instead of the MS5?
In the S-tool case throat, you mean?
Yes.
Yes. So with a new way of uplifting, the problem is that in this S-tool throat, the radius of the S3 at the tip is given by square root of K. So okay. You're not able to tune this radius anymore. So it's not possible to go arbitrarily close to this line.
So you cannot use, I understand. Okay.
Yeah. Yeah.
Because you don't have GS, which is tunable. It is you have just an integer number, essentially. Okay. Yeah. Okay, thanks.
Other questions? Okay. If there are no further questions, we can move to the next speaker. Thanks a lot again, Simon.